Alright, we will in the next lesson be using all these to solve problems. Let's now talk about energy of simple harmonic motion. You see, the simple harmonic motion is made possible by the changes in energy from potential to kinetic to potential and so on. So we must have a fair idea of how these energy changes take place. When a spring is compressed or stretched by a distance y, the work done is stored as potential energy of the spring. Is that right? When a spring is either stretched or compressed by a distance y, the work done is stored as potential energy. Do you remember the equation for potential energy of a stretched spring? We did that in Physics 1. U equal to 1/2 k y squared, where y is the displacement. You see? So, when a spring is compressed or stretched by a distance y, the work done is given by W equal to 1/2 k y squared. This is the equation we developed in Physics 1 using the method of calculus. Okay, k is the spring constant and y is the displacement. Okay, this work done is a measure of the potential energy U of the spring. So what is the potential energy of a stretched spring? The potential energy U of a stretched spring is U equal to 1/2 k y squared, where k is the spring constant and y is the amount of stretch or the amount of compression. If v is the velocity of the mass at that instant, then the mass will have a kinetic energy given by k equal to 1/2 mv squared. That means as the mass oscillates at any given instant, there is some potential energy in the spring given by 1/2 ky squared, and there is some kinetic energy of the mass given by 1/2 mv squared. So what is the total energy of the system at any given instant? The total energy is the sum of the potential energy and the kinetic energy. So I can write E, the total energy is U plus K, which is 1/2 ky squared plus 1/2 mv squared. Now we are going to take some specific positions and talk about this. Alright, let's do that over here. At the two extreme positions, what is the velocity of the mass? You see, at the two extreme positions, the mass will be momentarily at rest. The velocity will be 0. That means at those two positions, the energy will be purely potential. There will be no kinetic energy. At this time, its displacement is maximum. Is that right? When the mass is at the upper extreme, the displacement is maximum. In other words, this y will be equal to A. What do you call the maximum displacement? There's a name for that. It's called the amplitude. So when the mass is at the upper extreme, its velocity will be 0 and its displacement y will be equal to A. Therefore, what will be the energy at that time? There, its kinetic energy will be 0. At the upper extreme, the kinetic energy is 0. The potential energy, look at this. This will be 0 because V is 0. The potential energy will be 1/2 K. In place of Y, I will use A because at that time, the value of y will be the amplitude, will be 1/2 k A squared. The potential energy U equal to 1/2 k A squared. I hope you can read that in the recording. and K, the kinetic energy, equal to 0 at the upper extreme. The total energy at this time, therefore, is 1/2 Ka squared plus 0, because the velocity is 0. And so, the total energy at the upper extreme is 1/2 Ka squared. How about the total energy at the lower extreme? Will also be 1/2 Ka squared. Although the potential energy and kinetic energy keep changing, the sum of these two always remain a constant. The law of conservation of energy tells you that energy can change from one form to another, but the total energy remains a constant. So, if this is the total energy at any given time, this total energy must be equal to this total energy when it is at the upper extreme or at the lower extreme. Therefore, the total energy of oscillation at any given time can be represented by this, equal to 1/2 Ka squared. Alright, so if I ask you, what is the energy of oscillation, or what is the energy of a simple harmonic oscillation, you must tell me immediately, E equal to 1/2 Ka squared. Alright. When does the oscillating object have the maximum velocity? We talked about it. The object has the maximum velocity at the equilibrium position. As it goes towards both extremes, the velocity decreases, becomes 0, and then increases to get the maximum velocity at the equilibrium position. So at the equilibrium position, all the potential energy is lost. What is the potential energy at the equilibrium position? There is no potential energy because the spring is not stretched or compressed. At the equilibrium position, there is no potential energy. All the energy is kinetic. So look at this. At the equilibrium, kinetic energy is 1/2 mv max squared. Look at the way I wrote the velocity. The velocity at the equilibrium has the maximum value, so I wrote V sub max. Kinetic energy is 1/2 mv max squared. Potential energy is 0. So, now this is the case, the same case of the horizontal oscillation as well. Now, let's take the case of the horizontal oscillation and represent the energy changes graphically. Alright? An object of mass m is attached to a horizontal spring and is pulled to the right. That means x is the displacement there, and released. Alright? How do the potential energy U, kinetic energy K, and the total energy change as x changes? You see, when the mass is at the equilibrium position, x is 0. When x is 0, the potential energy is 0. The kinetic energy is maximum. When x is maximum, potential energy is maximum, kinetic energy is 0, and so on. Let's represent these graphically. Now look at this. This represents the variation of x. X equal to a cos omega t. Well, it means at t equal to 0, the object is at the right extreme. That's why we use the cosine function. This is a cosine graph. Okay, when x is maximum, look at the potential energy. Potential energy is maximum, kinetic energy is 0. There you are. Now, when x is 0, look at this here. When x is 0, potential energy is 0, kinetic energy is maximum. When x is at the other extreme, at the negative maximum, potential energy is maximum, kinetic energy is 0. Now, that means as x changes, potential energy changes, kinetic energy changes, but the total energy will always be the same. Look at this. This is a measure of the total energy, and that will always be the same. The energy keeps changing from potential to kinetic, but the total energy will always be the same. And what will be the measure of that total energy? It will be 1/2 Ka squared. Alright, look at this equation now. Kinetic energy changes, potential energy changes as the spring oscillates, but look at the total energy. Kinetic energy plus potential energy remains a constant. The kinetic energy changes, potential energy changes with time, but the total energy remains a constant. Alright, let's now obtain an equation for the maximum velocity of a simple harmonic motion. Where does the maximum velocity occur? The maximum velocity occurs at the equilibrium position. Since all the energy is kinetic at the equilibrium position, there is no potential energy. All the energy is kinetic. The velocity is the maximum there. Therefore, if V max is the maximum velocity at the equilibrium position, then the kinetic energy can be written as K equal to 1/2 mv max squared. The total energy at the equilibrium position, tell me, what is the potential energy there? Is 0. So the total energy is just the kinetic energy, 1/2 mv max squared. And you know that the total energy of a simple harmonic motion is 1/2 Ka squared. You see, that's equal to 1/2 Ka squared. You can now solve for Vmax. Can you do that? 1/2 and 1/2 will go. We can solve for Vmax. I'm going to leave it for you to solve that equation. You see, 1/2 mv max squared equal to 1/2 Ka squared. And therefore, Vmax equal to square root of K over m times A. Now, I don't think you will like me asking a question now. Some time ago, well, towards the beginning of this lesson, that was quite a while ago, over an hour ago, we obtained an equation for omega. Square root of K over m. Now, please go back and refer. It will be there. Square root of K over m is the same as omega. Alright, so replacing square root K over m by omega, we get V max, the maximum velocity is omega A. That's a very important equation. Alright, now